Welcome everybody to the virtual seminar of the International Institute of Physics. And today it's a great pleasure to introduce Julia Plavnik. Julia received her PhD from the National University of Cordova in Argentina, and she spent some years as a postdoc at the same university and at the University of Buenos Aires, as well as Texas A&M University in the United States. Since 2018, she is a mathematics professor at Indiana University Bloomington, and her field of research generally can be classified as representation theory, but more specifically, she works with quantum groups, knot theory, and related associated modular tensor categories. And in physics, this has applications in topological quantum computing with anyons in quantum Hall systems. Julia is a principal investigator in Simon's grant called Global Categorical Symmetries. She's also a recipient of National Science Foundation grants, and most recently, she received a fellowship from Humboldt Foundation, which means she spent some time in Hamburg in Germany. Today, Julia will tell us about mathematical framework behind the topological quantum computation. Thank you, Julia, for accepting our invitation. And without further ado, I pass the word to you.
Thank you so much, Dimitri, for the invitation, and thank you everybody for joining today. So I changed a little bit maybe the title, and I wanted to make a disclaimer. I will talk more about the algebraic point of view or the algebraic framework for topological quantum computing, this topological quantum computation with anyons. I will mention some other things. A lot of topology is there, as you could see in the name, but I will give you more the algebraic side of the story, which is the one that I focus on my research. Yeah, and I'm thankful for the Simon Foundation and the NSF for the funding. And yeah, I'm at Indiana University. So let me see here. Let's go here. So just to start, I wanted to mention what I mean when I say quantum computation. So I'm following this definition by Mike Friedman, Alexei Kitaev, Michael Larsen, who is currently at Indiana University, and Shenhan Wang, who was at Indiana University at that time, I think, and now he's in Microsoft, Station Q. So for me, or following this definition, quantum computation will be any computational model that it's based on the theoretical ability to manufacture, manipulate, and measure some quantum states. And let me just tell you a little bit about this prototypical quantum computation scheme that we will keep in mind. So we will start with a classical function. And what we really want to do is we want to compute the value of f at some n, some string n. And for that, what we will do is we will encode the information n as a quantum state. And then the idea is that n as a quantum state. So the idea is that we want to process that quantum state, and we get something out of this that will depend on the function of our initial function, our initial classical function f. And what we want is we want to be able to measure what we get when we find the quantum state f at n, and the probability should be AFN, and hopefully that will be with high probability. That's kind of the idea. So basically, maybe the logo or what we want to do is we would like to squeeze the classical information out of some quantum system. That's what we want, what we would like to. So let me tell you a little bit about this, and maybe people is familiar. We'll just repeat some things to get the idea on why topological quantum computation. But so the idea is that, for example, you could look at this quantum circuit model. So we will start with a vector space or a Hilbert space. In this case, will be the two copies of the complex numbers, the space V. And what we will do is we will look at the space of, or the state space, which are the n qubits, just n copies of this V. So what will be a quantum gate set? Will be a set of certain unitary matrices. I pick here 3 special matrices. I didn't wrote them there just for space reasons. U1 will be a 4 times 4 matrix. it will be the one called the control knot matrix. The U2 and the U3 will be 2 by 2 matrices, and the U2 will be the P8 or T-gate sometimes, and the U3 will be the Hadamard matrix for me, but you could have other different unitary matrices, doesn't need to be this. This one is for the last statement in the slide. So a quantum gate set just will be some unitary matrix, and what we want to do is we want to consider quantum circuits on this S. So we will consider n qubits, so length n, and what we are doing is we're encoding somehow locally the information of these quantum gates. So what we will do is we will have certain copies of the identity and one copy of this unitary operator, of this unitary matrix. And this will be or all these n qubits will be unitary operators from Vn for our state space of n qubits. And in this specific case, with the three matrices that I told you that I picked, the U1 being the control knot, the U2 being the T gate or the P8 gate, depending, some people know it with different names, and the U3 being the Hadamard. In this case, this gate is universal. And what I mean with universal is that any quantum operation can be approximate. It doesn't need to be equal. It can be only approximate by a sequence of gates in this finite set that I'm giving you. Okay, so that's kind of the idea, but let's make some remarks about this quantum circuit model. One of the things is that this is the setting of most quantum algorithms. For example, short factorization of integers is in this setting. But it has one big problem, that it's the coherence. There are a lot of errors due to interaction with the surrounding materials. And the problem is that the error correction cost for this is very expensive. Like one logical qubit will require many physical qubits. Some people think that the problem or why this happens is because local encoding, as we were seeing that we were doing this n qubits, and I told you that we are using one of these UIs, and so it's local, the idea. So this local encoding is vulnerable to local errors. So one answer to this, or one idea for answering this problem, is to use topology. And the idea is that we would like to encode this information globally instead of locally, right? So this will be fault tolerant just because it's constructed in this way. So it will be inherently fault tolerant. So that will be kind of the idea. So let me tell you about this ABC of topological quantum computing. And here I'm stealing this fantastic title that I love from a paper that it's in the bulletin of the AMS by Eric Rowell and Shenhan Wang. And the idea is that there are three basic notions in topological quantum computing. One is the one of anyons, the other is braids, and the other are categories. So how these notions appear. The idea is that the trajectories of these quasi-particles or these anyons that we will use, that we will have in our system, are described by functions or arrows in a certain modular category. And at the same time, we could think about that as words, these trajectories of anyons, when they evolve on time, the anyons, how they are moving, or the trajectory of them, these trajectories can be described also via the braid group. So a little bit here, I wanted to do this idea of the braid group, like you have your anyons and you are looking at the trajectories, and if you see there are some kind of braidings, there is a mathematical beautiful theory or a very nice object called the braid group, and you can describe this using the braid group. I don't know if you have any questions so far. Please feel free to stop me at any time with questions. So maybe I want to say a little bit more about this idea on how we use this topological quantum computing idea. So, and how we go from computation to the physics side and later to the math side. So the idea is that we will start with our system from the vacuum. So we initialize the system, and in the physics side, what we're doing is we're creating anyons. Once we have these, you see the anions come from in pairs. So once we have them, we want to braid the anions. And braid the anions correspond in the computational side to apply gates. We are really computing something. And at the end, we will have an output from our computation. And in the physical side, that it's measured. It's doing the fusion. So we are annihilating somehow our anions. And what we want is we want to measure the probability that, again, this is the vacuum. So this is kind of this idea. So I told you a little bit about this braid group, not much. But as I said, I will focus more on the algebraic side. And so I will focus more on the modular category side. So understanding these trajectories of the anions as maps in certain modular categories. Maybe before explaining more in detail what it's a modular category, let me say a little bit more about them. These are very nice algebraic objects. They are beautiful to study just because they are interesting, but also one of the things that for me is very exciting is that they are related to many, many areas of mathematics. So as I was mentioning before starting the talk, for example, they appear in different settings in analysis when you study planar algebra, subfactors theory, von Neumann algebras, operator algebras. There are things related to fusion, multifusion, and modular categories. And actually, a lot of the exotic examples that we have come from the theory of subfactors. Then you could have a more like low-dimensional topology approach, and you could be interested in learning about knots and link invariants, and modular categories also appear in that setting. Or from the mathematical physics side, when you study conformal field theories and vertex operator algebras. And actually, there is a conjecture that every modular category is the category of representations of a nice CFT, conformal field theory, but that's a conjecture for now. It's not known if it's true, but it's an interesting question. Or you can study them from maybe a more algebraic approach. For example, when I started studying this, I studied in Córdoba, my PhD, and there is a big group doing Hopf algebras there. Hopf algebras are very beautiful, non-commutative algebras, and the representation theory give you tensor, fusion, braided, or modular categories if you add nice adjectives to your Hopf algebras. And in particular, this is also related with the idea of quantum groups. So maybe let me say one more thing. This difference approach were very exciting. Like the theory of tensor categories was studied in the 60s, but then it was like bring to life again, I would say, or was was very interesting because in the 90s, 3 Fields medalists were given by topics related with this. So Witten, that was giving a physical connection with TQFTs, von Jones with the Jones polynomial, and also Drinfeld with the quantum groups. And then Reshettiken and Turaev put all this together with the notion of a modular category. So maybe let me tell you a little bit now. We were in the other side looking at computation and physics. Now let me tell you a little bit about anionic system and how, if you know about anionic system, you could translate into modular categories or vice versa. And I know I haven't given yet the formal definition, but I will give a definition of a category and a tensor category and more things soon. But I wanted at least for you to have this dictionary so you could keep this in mind if you're familiar with the maybe more physical side. So the anion types will be something called the simple objects in my category, in my modular category. These simple objects let me construct all the other objects in my category from them, using some operations that I will have. The fusion will be the tensor product in the algebraic side. The vacuum type or ground state, it's the unit for this tensor product, and it's actually one of these simple objects, so it's one of the anion types. The antiparticle will be a special object that it's called the dual object, and it doesn't come by itself. It's not just another object. It comes with 2 maps, evaluation and co-evaluation, which correspond to the annihilation and creation that we were looking in our drawing a couple of slides before, when we were initializing or measuring the system. Then the braiding will correspond to particle exchange. Anion types observable is related to the determinant of certain important matrix, which is called the S matrix. And I will talk more about this in a little bit. So here it's what anion types could be detected via braiding twice with any other anion. And basically what I'm saying is that the only one that I will be able to do it is the vacuum type. And then the topological spin, it's something that we call the twist. So let me see, I got a question in the chat. So anion have symmetry relation different from bosons and fermion. What is the equivalent for symmetry relations for modular categories? So maybe let me say a little bit about this. When we are in modular categories, we could detect, and that's kind of detected here in the twist part. Oh, sorry, I need to go one more. So we have twist, and the twist determine if our object, this topological spin, is a boson, is a fermion, or if it's something else. We call it boson in the math side when the object, when you tensor it with itself, give you the unit. But also twist need to be 1. And it's a fermion if the twist is -1. But this twist doesn't need to be only 1 and -1. That's, I think it's why it's called anion, but I'm not sure. It can be other phase, which will be a root of unity. It can be another phase. So the twist in this side will be just a root of unity that we attach to this and need to satisfy certain nice properties. I don't know if that answered the question in the chat. But if not, feel free to ask again or open the mic.
Okay, thank you so much. That was my question. So you are saying that twist is like a symmetry relation?
The twist, it's an extra structure that we are giving. I'm not saying that it's exactly a symmetry relation. I'm saying that it's one of the things that we look in this anion type. It's one of the things that we consider. It's another extra information that we look for them.
Okay, so maybe you can, in the while you go in your talk, give some references
yes,
which make the correspondence between modular and anion.
Yes, I can send you some reference. I can put them in the chat.
Thank you, Sam.
No problem.
I think twist is just the braiding operation. You can think of this as a braiding operation on anions.
It's not exactly the braiding. The braiding, it's like interchange 2 anions. The twist is something that only consider 1 anion. And in principle, the idea is that it's measuring some spin in many cases. So when you look at the twist of X of one of these simple objects, that will be a complex number, and it will be a root of unity. All of them will be root of certain unity determined by the category. And actually, we put them all in a nice matrix, which is called the T matrix. And I will show you a picture in a little bit.
What I'm saying is that this braiding matrix has eigenvalues, and I think eigenvalues are these complex numbers that you are talking about, because they in fact characterize anions or type of anion.
Yeah, you are mentioning, okay, I didn't understand what you are saying. Yeah, you can compute the twist by looking at the braid of X and X with itself. Yeah, X with itself, and there is a way to compute the twist out of it. Yes, sorry. By the same, only one of the anions. And I will show you a picture in a little bit about that.
Julia, good afternoon. Thank you for this talk. Dimitri, I am wish this space just to make a question. Julia, as you said, we could do questions. How do you know that this mapping, this dictionary, is a relation 1-to-1?
I think this, I don't know if there is exactly mathematical proof, but it's believed between the expert that this is kind of the correct dictionary, not for any. So what it's believed, and I will say a little bit, not a little bit more, but it's one of the kind of questions. How can we model certain things, right? And one of the questions was, how can we model two-dimensional bosonic topological phases of matter? And the answer is that in that case, or what it's believed is that in that case, the correct way to characterize them are by these modular categories. And if instead you want to characterize fermionic, here we will need to use something called supermodulars. But I think that's what most of the people think. I don't know if there is a mathematical proof for that, to be honest. But that's kind of what it's believed, that when you are doing two-dimensional topological phases, you can describe them using these modular categories. In the bosonic case and in the fermionic, you can use supermodular.
I think maybe, I'm sorry for the comment, but I think here Fabio should probably read the citation of Dirac on one of the previous slides, who said that mathematicians, they follow the rules of the game, following maybe just considerations of beauty, and physicists, whatever nature provides for them. So we're here talking about beauty, and then, you know, if, whether physics, real physics, realizes this beauty or not, that's a good question. But according to Dirac, it does.
Yeah, I put that as not. Yeah, I like the quote. Yeah, some physicists, I don't know, like Xiao Gangwen and some others, I feel like Kitaev, and these people have this idea that probably this, or that modular categories are the good objects to describe these anionic systems, especially these two-dimensional like bosonic topological phases. I'm not 100% sure if there is a precise proof, let's say. At least what I would say is a precise proof. I don't know if it's just the theory or if, but I think that's it's something that most of the experts, I would say, that coincide that this is like the correct notion to model them. That's what I would say, but I could try to see if there is a good reference and send it later to Dimitri about that.
Right, thank you, Julia, for your attention. Dimitri, good comment.
Maybe something that I can add, it's that another way that sometimes they think about these modular categories, it's the TQFT, the topological quantum field theories. And sometimes that maybe it's easier to relate with these. I don't know. And yeah, and modular categories and TQFT, there are, they are related, and maybe that's more like a mathematical theorem. I don't know exactly, the physical side. So yeah, and thank you for the questions, and please keep going. And I will look for the reference if I don't know it by heart. So maybe I wanted to give you the definition, more like the precise definition of a category, because this is the mathematical object that we will be using. So a category is just a collection of objects and a collection of arrows or map between the objects that we have. There are some rules that these things need to satisfy. First, these arrows have a composition, and that composition is associative. And the other thing that happens is that if you give me one object, I always have the identity arrow for that object. So I look at objects, I look at arrows, I can look at the collection of all the arrows for the objects, but one important arrow that it's always there is the identity of each object. That's the idea. In the categories that we will be studying, these are called small categories. So everything that we will look at, objects, arrows, all of them form a set. There could be more strange things happening. Some examples to keep in mind are this one here, but before going to the examples, maybe let me say a little bit more about this idea of object and arrow. Like when we studied in math things, usually we start studying some object, right? What I mean is something with certain structure. For example, you can study topological spaces. And topological spaces are certain sets that satisfy something, right? That have some property that we care about. So when we want to compare the different topological spaces, what we do is we look at the functions between them. And in this case, we look at functions because, as I said, topological spaces are sets with more structure. So functions are the things that relate sets, right? When we want to compare two sets, what we look at are the functions between them. That's this first example is the category of sets. So the objects are sets, and the arrows are the functions between the sets. And that's how we compare sets. We know if a set is bigger than the other by looking at if the functions are injective or not between them, things like this, right? Now, when we go to topological spaces, we're kind of upgrading. Not exactly, but we have the sets, but now we have extra structure of them. So we have this notion of continuous, right? And so when we look at arrows between topological spaces, we want functions that preserve that, right? We have the open sets and we want a continuous function, something that respects this, the set to be open, right? That takes opens in opens. So that's kind of the idea of category theory. We have objects that we want to study, and to compare them, what is important is to understand the maps between them. That's why the arrows or maps or morphisms, I will use all these different words, are very important, are kind of the key part of the categories. And in these examples, maybe, or in most of these examples, you will see that you have elements in your in the objects that you have. Like if I give you a set X, probably you can see what are the elements in that X because it's a set, right? But in general, in category theory, we usually don't care about the elements that are inside certain objects. Some objects don't have elements. What we care are really the functions between them. So a lot of the time when we want to describe something, like for example, the image, we don't use the elements, but we use something called a universal property. We use some property of the maps to describe something that we want. It could be a property, it could be some other special object or things like this. So here maybe let me say some of examples. Set and topological spaces I already said. So set are, the objects are sets and the maps are, or arrows are functions. Topological spaces, the objects are topological spaces, as the name says, and the maps are continuous functions. The third one is, the GR is groups. So the objects are groups and the maps are what it's called group homomorphisms, which are functions that behave well with the product. So if you give me two elements in my group, I can multiply them, I can apply the function, and now what I want is that the function at the product is the same as the product of the function at each of the elements. And then this ab here means the category of abelian groups. So the objects are abelian groups. Abelian means that the product is commutative, but the arrows are just group homomorphisms. Why? Because being abelian is just something that you check. It's a property of the group. And when you look at the function, you don't need to ask something extra. Not like here that we want to preserve this extra structure that we were giving to my set, that it's having these open sets. It's just something that you check. It's commutative or not. And so when you apply the function, you don't need to ask this to be preserved. It's something that will come for free. And this last example, it's G. Let me give you this example more in detail. For me, G will be a group. And I want to look at this group G as a category. There are many ways to look at this group G as a category. Disclaimer, I will do one example. So the objects in this category G will be just one object that I will call star. It doesn't matter, it's the category with one object. So I told you, for giving you a category, I need to tell you who are the objects, who are the arrows, and then who is the composition. And then it needs to satisfy these other two things, that the composition is associative and that I have an identity arrow. So I told you I have only one object. Now I need to tell you who are the arrows between the objects. In this case, only the arrows between star and star. So what I will call my arrows will be just the elements in my group. And now the composition is the product in the group. The product in the group is always associative because that's one of the things that we ask for a group. And the identity will be the neutral element in the group. The neutral element is an element that when I multiply it with any other element in the group, I get the same thing that I gave to this element. So this is it's a funny example of a category, but there are many other categories. This category looks a little bit boring, but they are not, but there are other examples just for you to know. Maybe one last thing about, so there are two other things that I want to say about category theory. One is that category theory is a very exciting area for many reasons. For some people, it's very abstract and they call it abstract nonsense. But what is nice about category theory is that powerful because sometimes you prove something about the class of categories. And then when you specialize to the category that you like, you get a result. For example, for many things that we like, I don't know, groups, rings, modules, there is something called the isomorphism theorems. And this could be proved in each category, or you could do a more categorical proof and then have it for free in all the categories that satisfy certain property. So it's something that let us prove things in different areas of mathematics at the same time. That's kind of one of the nice things. The other thing is that asking for equality of objects is too much. We usually don't ask for equality. Instead, we use the arrows. Because I told you here, the most important things are the arrows. So instead of asking that two objects are equal, usually what we ask is that they are isomorphic. Isomorphic means that I have there is some nice definition, but if you think about sets, what it means is that the functions is bijective. And if you think about topological spaces, again, you think about continuous bijective functions and like this. So it's kind of this idea of bijective, of you want these two things to be kind of the same, but instead of asking equality, you will ask something slightly less restrictive. So maybe now let me give you a nice example of a category. And I think this is a nice example because maybe people is familiar and I will tell you another ideas on how to think about that, but also model some of the things that I want in the categories that I will work with, which in some sense seems very complicated, the categories that I will work with, because they have a lot of structure. So I will need to give you the definition. I will need to tell you a lot of adjectives that I want, but actually that makes the category easier to work with because it has a lot of structure. So I have a lot of tools to work with. So the category vec for me will be the category of finite dimensional vector spaces. Here I'm cheating a little bit because when you have a finite dimension, or when you have a vector space, what is a vector space, right? It's a set with two operations. One is I want an addition, but the other is I want an scalar multiplication. So I need to tell you who are my scalars. So here I'm cheating, but I do have a field. Maybe here I should have say category of finite dimensional K vector spaces, where K is my field. So this K is my field. And I will tell you a little bit why I want a finite dimensional. But this generalized to many other things like Hilbert spaces and other categories that are more complicated. So if you are familiar with group theory, you could use representations of a finite dimensional group. And if maybe thinking about any K, it's a little weird, thinking about the complex numbers is perfectly fine. Here, it is important. It's very different if we think about K being the complex or being the real numbers. If we think about the real numbers, a lot of things break. So we would like to think about fields that are called algebraically closed and of characteristic zero, like the complex. So I would say maybe better to keep the complex numbers in hand. Like instead of K, think about the complex. So what are things that are nice about this category? First, who are the objects? Finite dimensional vector spaces. Who are the morphisms? Are these that I wrote here, the linear maps between V and W. So if V and W are two vector spaces, I want to consider who will be the arrows in my category, just the maps or the functions that preserve that structure. So they are linear maps. So what are nice things that I know about this category? The first one is that I could do the direct sum of vector spaces. So if I have a finite dimensional vector space, basically I can think of it as if it has dimension n, I will have a basis of n vectors, v1, v2, vn. And basically what I'm saying is that my vector space looks like n copies of the complex, right? Or of the field that I'm working with. So now, what is the direct sum? It's a new vector space that has dimension n plus m if the dimension of V is n and the dimension of W is m, and the bases are given by the basis of this one union the basis of this one. So that's nice. I have a new vector space that I can create in this way. The other vector space that is there is the zero-dimensional vector space, which is just empty. But this zero-dimensional vector space is nice because it behaves nice with this sum. It's actually the neutral element for that sum. The other nice thing is that if you look at the maps between two finite dimensional vector spaces, if you look at the linear transformations, linear maps, the set of linear maps is a vector space itself. And again, it's finite dimensional because V and W are finite dimensional. The other very nice thing that I can do is if you give me two vector spaces, now I can get a new one, which is the tensor product. And this one will be a vector space of dimension n times m. And there's again a distinguished vector space, which here we could think about the complex directly, the one-dimensional vector space. And that one-dimensional vector space is very nice because it's the unit for this tensor product. That's kind of the nice thing. And here, as I was saying, I don't care about how you give me the one-dimensional vector space. I just care that it's isomorphic, that it's equivalent in this way to the one-dimensional vector space. That's why I say it in this way. One very nice thing about this one-dimensional vector space is that you cannot have any other subspaces inside the one-dimensional that are not the zero or itself. When that happens, we call the object simple. When there is nothing inside that it's not the zero, which is always there, or itself, we call it simple. There is another question. Can we thus define VEC as being a category with the exam of tensor product as morphisms instead of a linear map? A category with the exam. I'm not sure if I understand the question, but this being a finite dimensional vector space is a coincidence that I'm looking at finite dimensional vector spaces and that the arrows are finite dimensional vector spaces. I will change who are the objects later, but I will still ask that the arrows are vector spaces. I don't know if that helps. So I'm trying here to give an example of a category that has nice properties that are the ones that I want later in my modular categories. So I don't
I think
always...
the question is, I'm sorry, I think the question is whether can you consider some of the vector spaces as a morphism, as an arrow, or a product? Like if you look at just the direct sum, is it a morphism or not? Can you view it as a morphism?
Probably yes, because I mean, if you look at V, you could look at V as a morphism because V is V is just isomorphic to V dual, right? And V dual is linear maps from V to the field. And so you will be able to look at us at morphisms. I don't know if that's the question, but the vector spaces will be able, in this very special case, to be. So in this very special setting, the objects will be maps, but it's a coincidence. In the general example that I give, which is representations of a group, here you have another kind of arrows, and they are still, they form a finite dimensional vector space. It's not like I always want my morphisms to be objects. It's just a coincidence in this case because the objects are, I don't know if that, I don't know, Rafael, if that answer. I saw that you say that it's what Dimitri is saying. In this special case, yes, the direct sum will be some linear maps, will be lean from V plus W to the K, to the field or to the C in this case, but it's because the objects in this case are finite dimensional vector spaces. But later, when I define the notion of a tensor category, the objects don't need to be vector spaces. And I will give you examples on why they are not always vector spaces. I will give an example. But what will happen is that the set of arrows in my category, they will always be vector spaces. In general, the set of arrows are, the arrows form a set. And in principle, that's it. But what I will ask is that these categories are enriched, have more structure. The morphism, instead of just being a set, I want them to be a vector space. It's a bad coincidence that in this case, the objects are also vector spaces, but in general, they won't. But thank you for the question because helps to clarify this, which I will say in the next slide also. So the other nice thing in this particular case, as I told you, a vector space, it's determined basically by the dimension. So if you give me this nice object, which is the field, the one-dimensional vector space, which is a simple one because it doesn't have anything interesting inside. In this case, any vector space can be written in terms of that one. How? I will have as many copies as the dimension of that vector space of the one-dimensional vector space. How I get this is just using the basis. And then here, this is very important. My vector space always has a dual. What's the dual is looking at V, comma, the field, right? Or the one-dimensional vector space. That's fine, that always happens. But when it's finite dimensional vector space, I can get also a co-evaluation map. The evaluation map, it's always there. What do? You give me a linear functional and you give me a vector, I plug it in. I evaluate the function, right? That's always there and I will get something from the field. But now I can go in the opposite direction. Going in the opposite direction, I'm not explaining here all the details, can be only done when the vector spaces are finite dimensional. Why? I mean, there is one easy way to go back. You give me the number 1 and where I send you back is to the sum of a basis of V tensor the dual basis. And you could ask, okay, it's true, this works for finite dimensional because I have a finite sum. Why it's needed? Because I'm giving you one formula for finite dimensional. It doesn't mean that I didn't prove that doesn't exist later. What I'm cheating here is that I'm not telling you these maps need to satisfy something called the zigzag. Basically, using these maps, I could start from B and end back in V, creating and annihilating things. And I want that map that I can create and annihilate to be the identity. I didn't write this here because it's technical, but that's what happened. And that's why finite dimensional is needed. Otherwise, many of these things you can do it anyway. And the last thing that I want to mention is that this category is nice because it has a swap. Like if you just switch the order of the product, you have a map from V tensor W to W tensor V, and it's an isomorphism. Because to be an isomorphism just matters the dimension in this category, right? Or not only, but in this case, it's an isomorphism. You are sending basis to basis, basically. So we have this nice thing that makes our tensor product described here commutative. So this is an example of what a modular category is. This is the smallest and more trivial, maybe, modular category that you have. More trivial because here the swap is very nice behaved just because the category is small. But I will tell you a little bit more in a minute about the definition. I don't know if you have questions. Yes.
Yeah. Are those evaluation and co-evaluation maps inverses in some sense?
No, in general, or depending how you think of inverses. I mean, they have different. You see that
if I compose them. Will I get?
Yeah, but you see that they don't go to the same thing.
Sure. I mean, in both separate spaces, right? In K and V tensor V2O.
Yeah. So they are almost like identities, and that's the zigzag equation. Let's see. No, I cannot do this. So the zigzag, what it tells you is that if you start with the V, if you start with the V, what you can do is saying V tensor K, because I told you that this K was the unit. V tensor K is isomorphic to V. So if you start with V, you use this unit, and now you use the co-evaluation, and you start in V tensor V dual tensor V. And now you use the co-evaluation, the evaluation, and you end in V tensor, in V tensor K, which is isomorphic K. To V, and that's what gives you the identity. So they are somehow inverses to each other, but you need to have the V there to make it really an inverse. The statement is not like if you compose them directly. Maybe let me see if I can annotate here. I never did it in live, but let's see if I can. So the idea is that you will have V. And instead of looking at V by itself, you will think that here I have K. I'm sorry that my handwriting with this is not the best. And this is permitted because this is really isomorphic to V, right? And now that I have the K, I can use the co-evaluation, and I will change this, you see, and I will have V dual. I will not do the tensor just because I'm slow, and V. And now, and that's why it's not exactly the identity, because if you see this V here, I'm using it now here, right? And I will use this piece. And what I will do now is I will use the evaluation there. So I will get VK. And I want this to be the identity. So it's not like I did, because if I were doing evaluation and co-evaluation, I would be using this. No, sorry, I didn't want to do that. Undo? No, okay. Arrow, maybe vanish pen. No, okay, I don't know how to do this, but so what I meant here is that I don't know if it's clear, but these two are the ones that come from the co-evaluation, and I don't use again the same thing to get to the evaluation. I use this other V that I have there from before. And when I do that, I get the identity. Otherwise, no, or the identity of V. Otherwise, I don't get it. So it's not exactly like they are inverses of each other, but they are kind of inverses of each other. I don't know if that makes sense. It's not exactly if you compose, you get the identity, but there is a trick to get something like that. That's the idea. It's kind of an inverse.
Yeah, I get the point. Thank you.
Okay, perfect. Thank you. Thank you for the question. So now I want to give you the definition of braided fusion category, which is, I don't know how to delete this that I did. Okay, let me see if I can. Okay. I never used this annotated before, and now. Okay, I will leave it for now there. If someone knows how to delete it, can tell me. So here I wanted to give you the definition of modular category, but I will give you first braided, and then I will tell you what means modular. So the first thing is that I want the same as in the category of vector spaces, but a little bit more general. So I want to have a category that has direct sums and a zero object, like we did have before. And I want that the home spaces, these are the spaces of arrows, are vector spaces over a certain field that I fix at the beginning. But now the objects don't need to be vector spaces. So in general, it's not like I can realize any of my objects as a morphism space. That's not true. That was a very specific coincidence of this example, okay? I'm sorry, I forgot this. Then the other thing that I want is to be able to express any object in my category as a finite sum of these simple blocks that I have, these other objects that don't have any object inside other than the zero and itself. So what this gives me is super important. It let me do linear algebra in this higher dimensional setting, basically. Because now, since everything is semi-simple, when I want to describe a map, it's enough to tell you how it's in the simples and then do some sum of them. Okay, so a lot of the things that I will need, I will be able to express them as matrices. And that's very useful because then what you can do is you can use the computer to solve things. Sometimes it's still very hard computational, but at least we have the computer to help us because we have semi-simplicity. Otherwise, this will be much more complicated. The next thing that we have is the tensor product that remember I had before. So I want to have a tensor product. I want that tensor product to be associative. And again, now I cannot ask for equality, so I ask for some arrow here that let me change parentheses from left to right. Let me see if I can. Hold on. So sorry, I saw how to save that. The next thing that I want is that remember that the field, the one-dimensional vector spaces, was a unit for this tensor product. Okay, I will ask the same. I will ask that I want a distinguished object in my category to be the unit. Now, to say that it's the unit, what I need to say is that x tensor 1 is x and 1 tensor x is x. I cannot say that they are equal, so I will ask that they are isomorphic using two maps, L and R. Moreover, I will ask that one of these simples here that I have, it's this unit. I will ask that this unit doesn't have any other sub-objects than itself and the zero. I will ask for existence of duals for every object in my category. And again, this evaluation and co-evaluation are these special maps that are inverses, but not exactly. They have this more complicated inverse idea behind, but that's the idea. The other thing that I want to ask is that in principle, I told you that I need finite direct sums here, but also I will ask to have finitely many of these simple blocks. And this number of simples will be called the rank. And it's an important thing that we use to classify categories. The other thing I was saying, up to here, I ask for a fusion category. If I drop semi-simple, this is called finite tensor category, that it's also interesting, for example, in logarithmic conformal field theory. Or if I drop the one being simple, this is called multifusion, and it's also interesting for subfactor theory, for example. But once I have this fusion, now what I will ask is that my tensor product is commutative, this tensor product. So for that, I will say that V tensor W is isomorphic to W tensor V. This is called the braid. It's an isomorphism, and it's not just that. It's not only at the level of the fusion rules that it needs to be satisfied. It needs to behave well with the tensor product. And from here, when you want to write this, you get something like the braid equation. So this is very related with braid group representations and with the Young-Baxter equation. Now, what I'm missing to say modular, I'm missing one condition about the braid and one condition related with the twist that we talked about before. So let me maybe say something else. So there are some important invariants that we look when we study this category. What I mean with invariants, I mean some numbers or some data that I can extract from my category that don't change if I have two categories that are like the same in my opinion, meaning equivalent tensor categories. So the first one is that I will look at the simples in my category. I told you these are finitely many, and one of them need to be the unit. And one important invariant is the number of these simples, that it's the rank. So how many anion types I have, basically. The other thing that I look is if I have two objects, I can do the tensor product. Now, this is a new object. This will be simples, as you saw here. So I do the tensor product, I get a new object. That doesn't need to be simple anymore. And then it's decomposed because my category is semi-simple as a sum of simples. Here I'm taking the anion types, and here these numbers, the nijk, are the number of times that appear this xk. So these are natural numbers of 0. So what we do is we look at the left multiplication by one of the simples, and we create a matrix with respect to this basis that we can look at, and we get what it's called the ni matrix. And basically what we have in that matrix are the fusion coefficient here. And that's nice because these are natural numbers or 0. And there is a theorem by Frobenius and Perron that proves that if you have one of these matrices, there exists a maximal non-negative eigenvalue, and it's always a real number that it's bigger or equal than 0. It can be proved that if the object is simple, this number is always positive, actually. And that's called the dimension, the Frobenius-Perron dimension of the object. And we can define, using the square of the dimensions of the simples, or the sum of that numbers, the dimension of the category. And these are very important invariants. There are other notions of dimension that are also very important. So maybe let me tell you fast 2 examples. I know that we are on time, so I don't know if I should finish now, Dimitri, or if I have 5 minutes.
Yeah, you can certainly have 10 more minutes because of the delays and questions.
Okay, perfect. So I will give you very fast examples just to show you that this doesn't need to be vector spaces, always the object. For example, there is a very beautiful category that is called Fibonacci. It has only 2 simple objects, rank 2. So I have colors 1 or anion types 1 and tau. And actually the dimension, this Frobenius-Perron dimension of tau, is this beautiful number, the golden radio, the 1 plus square root of 5 over 2. And the fusion, I just need to tell you how fuse tau with tau because the unit fuse always trivially. So tau, tensor tau will give you 1 plus tau. And there is a nicest matrix using the golden radio and some ones, and the determinant, if you compute it, is different from 0. This determinant being different from 0 is very important. But this is a beautiful category. The Fibonacci numbers appear as fusion rules when you do more powers, or as dimension of home spaces, also if you keep going. So another example it's the easing category. So in this case, the easing category has rank 3, and the simple objects are 1, sigma, and C. C is dimension 1, which means that you can prove that this object is invertible. X tensor X dual will give you 1. And when we have that happening, we name the object invertible because it has the dual is the inverse for the product. But this other object has dimension square root of 2. Here I wrote the fusion rules and the S matrix, which is again different from 0. And let me go back 1 second here. So this dimension is very important. First of all, I'm telling you that from this dimension, you can determine if the object has an inverse. The dual will be an inverse if and only if the dimension of the object is 1, which is already something nice. But actually, the dimension of this object will be an integer, which in general is not needed because you saw that they could be real numbers. I show you the golden radio or the square root of an element. The object, if you want your object to have an underlying vector space structure, you need, for having any hope, you need the dimension to be an integer. So these two categories don't have objects that are vector spaces in general. For example, this one doesn't have a vector space underlying. It's not a vector space, okay? So that dimension is a beautiful thing to look at. So maybe let me say a little bit about knot and link invariants. I didn't tell you yet what it's modular, so I'm almost there. We want to have a trace in our category. We want to be able to take trace of the morphisms in the category. And for that, we need an extra name, which is called ribbon or spherical structure. And it's given by this twist that I mentioned before. When the twist is beautiful enough, which means spherical, I can take traces. And that let me compute some knots and link invariants. And what I do is you give me the knot and link invariant, and I think of this as a closure of a braid word, and doesn't matter which side I close it. In principle, in general, I should close all on the right or all in the left if I have pivotal, but if I'm in an spherical, so the twist is very beautiful, I can close it in any way. It's like the closure lives in this sphere and I can move it and it doesn't change, basically. That's kind of the idea. And let me compute knots and link invariants. So let me give you an example. So the S matrix is recovered as some trace, and here for me trace plus and minus will be the same because I'm spherical, of this nice Hoff link. I give colors, which means just one of the simple objects or the anion types to each of the strands. And this map that if I cut these opens, if I cut this closure of the words, you see here I have the interchange between the X and the Y, and here again I have the interchange. So what I'm doing is the braid 2 times, which in the other slide sadly I call sigma, but in this picture I have a C. But the C is the braid here, the interchange between X and Y, that I want this tensor product to be commutative. And when I take the trace of that, that gives me the S matrix or the entry XY of the S matrix. This is a very important matrix. The other one is given by the twist. And as Dimitri was saying, you can compute it using the self-braid, but you need to normalize by a certain number that it's called the quantum dimension, which is the value of the circle for each object. And something I mentioned a lot of the time, that being determinant 0 is very important for the S matrix because that determines that the category is modular. So for being modular, you need braided. You also need spherical, so I can take traces. And now I need that this determinant is different from 0. Then the other comment is that this S and T matrix give us a lot of information that comes from modular group representations and a lot of number theoretical information. And let me just comment a little bit of what we care about and tell you some results. So one of the things that we care about are, for example, one of the questions, it's what could be an algebraic model for 2D bosonic topological phases? And the answer, it's these modular categories or this TQFT. The other could be classified, which is a little bit harder. We want something like a periodic table. So, right, you have an element in nature, you would like to say some things. For example, the number of simples, the dimension, the S and the T, the fusion. Some of these can be deduced from the other. For example, if you have the S, you can recover the fusion rules. Or the rank is also given by the S matrix and the dimension also, but S and T are not enough to distinguish the category. I can have two categories with the same S and T, and they are different categories. So spoiler, we need more here. And actually, we are studying other links and nodes, because as you saw, the S and the T come from these two beautiful links that we have here, and nodes, but we need more to understand. Other kind of questions are more in the quantum information side. We want universality of the gates, for example, and that seems to be able to be detected by the Frobenius-Perron dimension. There is a conjecture by Eric Rowell that universality follows from having dimension of the category not being an integer and vice versa. But that's a conjecture, so we're still thinking if this is true. And we also would like, these onions are point-like excitations or point-like particles. We would like to know what happens if we change that to more, like instead of two-dimensional, three-dimensional generalization, for example, loop-like particles. And there is a lot of study of loop braid groups and another motion groups instead of the braid group. And maybe let me finish with some results. So for the periodic table side, for the classification program, and here I'm giving just a very small sample, we try to classify by rank, meaning number of simple objects. For modular categories, at the moment, there is just a classification up to rank 6, so not very big. If you add another condition that it's that this dimension is a number, an integer number, and it's odd, with Agustina Senki, we have pushed that up to more or less 23. Published up to 15, but we push it up to 23. So if you have that condition, it gets much longer or much larger, the classification, but still we're in the early stages, as you can see. We also classify by Frobenius-Perron dimension or by quantum dimension. The quantum dimension is slightly harder. And then constructions, other thing that we love to do, because this is a very young theory. I told you, we only know up to rank 6, which is small. So we don't have a lot of exotic examples. The exotic examples, and with exotic, I mean not coming from quantum groups. There are some examples that we think are exotic coming from centers of subfactors. So what we try to do is get new categories from things that we know. So for example, the Drinfeld center is a classical construction for monoidal categories. Equivariantization, which is taking fixed points under certain action, or Orbifold, if you're familiar with that, it's related with equivariantization and with gauging, extending the theory, or something called zesting. So these are the kind of things that we have been doing. Thank you for listening. Sorry that I went over.
Well, thank you, Julia, for this very nice introduction and categories and relations to quantum computing. And so let us see if there are questions.
I can stop sharing. While you ask me questions, I can share again if needed.
So I have maybe let me start. I have a question. So first of all, about this classification, you said you have 15 different, well, depending on how you classify them, there are.
No, I was
15.
saying that, for example, the rank, it's the number of simples. For example, if you only ask fusion category without a braid, we only can classify if it's rank 2. So I can only tell you a list. Classification means that I can give you a list of the things that I know, or not that I know, that we have a complete list of all the things that have this property. Rank means two things, means having two of these simples. So for fusion, we only know up to rank 2, which is just being the representations of set 2, or being basically Fibonacci, which is the one that I show you. If we add the word modular, we know up to rank 6. It's not like we have 6 things. It's just that if you give me categories with 1, 2, 3, 4, or 5, or 6 simple objects, I can give you a list of all the possible ones. And if you add the condition of being odd dimensional to the category, I can give you this up to rank 23. But it's not like there are only 23. It's more like we know, like, for example, in vector spaces, what I mean with classification, any vector space is classified by the dimension. So if you tell me the dimension, I know what the vector space looks. It's enough to say the dimension, right? That's what classification means. In this case, we are trying to classify by rank, because classifying in general is impossible at the moment with the tools that we have. So we put conditions. We say, okay, I only want to classify things that have 6 simple objects. That's kind of what we are doing in this item here.
But is there any relation with classification of conformal field theories, for example, like rational conformal field theories, for example?
Yeah, C2 finite rational conformal field theories, the representation theory of them give you a modular category. So it's very closely related. So if you have but it's not completely, so it's closely related, but it's not known if every modular category comes from them. So that's, for example, one of the justification of looking at classification. Maybe we classify and we see that there is not exactly the same thing, that we get more things in our setting, or maybe not, maybe it doesn't happen, and maybe it's the same CFT than MTCs.
So my question is like naive. So there's infinite number of rational CFT, for example, and now you're talking about finite number of.
Okay, I can tell you something. I can tell you something about that. That's an excellent question. What conjectured by Shenhan Wang here, and proved by him, Eric Rowell, Richard and Paul Brulliard, was that if you fix the rank, so if I say, okay, look at all the modular categories of rank n, are there finitely many or not? He conjectured that there were only finitely many of each rank, and the answer is yes, for modular. So maybe you find a lot of CFT, but when you fix the rank, the representation theory that have that rank, it's only finitely many representation theories that are different, because you could have two VOIs CFT that give you the same representation theory, or equivalent, right? Even if they are different. For example, for Hopf algebra, we know very well when the category of representation give you the same thing or not. It doesn't need to be different as Hopf algebras. The same as Hopf algebra to give different, or the same representation theory. You could have different Hopf algebra that give you the same category of representation. So it's a little different how many lead to the same thing, right?
I see. Okay, I understood. So there's a question from Tiago Pernambuco in the chat. So I think he wants to know if you can connect this to this quantum computation really in different gates like C0, Hadamard, and others.
Yeah, basically what you will need to do is when you are looking at let me go back. At this thing, you will need to give values here, right? And could be these gates, but at the same time, this will be braid onions or the braiding of onions. So this will be connected to some of the maps that we have in our category. I myself don't do this part that much. I work on this side, but they are trying really to do it even in the lab. They are really trying to construct these things, right? For example, they know, let me go back, because they want universal things, right? So for example, this example will be universal, or it's universal. They prove that this could give you something universal, but this one won't. So they are really trying to find, maybe not exactly this, but things like this in the lab.
So dimension of the category is the sum of the squares of the dimensions of the
Yes.
simples? Okay.
Yeah, in this one it's harder to compute, but in this one, for example, you sum the squares, so you have, this one always have dimension 1, this one has 1, so 1, because I square it, and this one has dimension square equal to 2, so the dimension of Ising is 4, for example. And here I wrote 1 Ising, but there are actually 8 modular categories like Ising, and they are all different because they change by something called the central charge, which I didn't introduce here. And something nice, for example, that we did is showing that this construction setting relates that 8 Ising that you have. And yeah, it's one of the things that we did.
Well, maybe adding to your answer to Tiago's question, I came across a paper which was trying to construct this standard gates of quantum computation like C0 and others in terms of braids. Well, I didn't go follow all the details, but well, they were even drawing like some very complex braids that would simulate this kind of operator. So people indeed study this kind of things.
Yeah. And for example, this one that I show you that it's bad for universality, the Ising, I said that this is bad for universality. Oh, sorry, it's somewhere here. They prove that if you have this and also you allow measurement, then it becomes good for universality. So you could get something universal even if this by itself doesn't give you. I wanted to find the reference because I know that I mentioned at least some references. And then I didn't send it in the chat. Or I could send it to Dimitri, but one, maybe let me stop sharing for a second and look it online. One nice, maybe long, it's the bulletin talk by Wang and Eric Rowell. Let me see if I can find it quickly, the link to archive at least. But there are a couple of this one is nice. I will send the archive link, but there are others. I know that Colin asked me for the links. And there is another one that, so let me see if I can find it quickly, that it's more new, but it's about breathings and motions. So this might be helpful with this idea of the last question by Tiago. Sorry. It's about breaths, motions, and topological quantum computation. And also by Eric. I think that two are nice references, but I could look for more. These are more like panoramic references, if that helps. And if not, feel free to send me an email. I would be happy to send more references.
Okay, I'm also copying the references. Thank you, Julia, for your talk. I do not see other questions. So thank you everyone for participating today, and Julia, thank you for the very nice talk. And I hope to see you again.
Yes,
next
me too.
week we have more seminars.
Thank you so much for the invitation. And we also have a seminar going on that it's math, physics, and things. Like I should maybe also add that in the chat. I think I added it.
If you like modular tensor categories and fusion and other categories.
Yeah, we have different things, some condensed matter talks, but also a lot of tensor categories and a lot of different things. So and it's a pleasure. Thank you so much for inviting me. Great. Thank you for the many questions. I hope to see you again.